Welcome to This Explainer. Today, we're setting the stage for an incredible journey into the absolute extreme edge of modern automotive design. We're looking at a machine that is literally forcing us to question the boundary between mechanical engineering and human physiology. It's the story of a vehicle that bends the laws of physics and, well, the fragile biological hardware that's us, the humans, strapped inside it.
So, it sounds like a physics-breaking glitch in a video game, right? Can a car actually drive upside down? We've all heard those late-night theoretical arguments that high-performance race cars generate enough aerodynamic downforce at top speeds to, in theory, drive on a ceiling. But it was just a theory, until recently. Over at a facility in Gloucestershire, a British automotive company took a purpose-built platform, drove an all-electric hypercar up a ramp, rotated the entire platform until the car was completely inverted, and the driver just drove forward. The car didn't fall, it was secured to the ceiling entirely by its own artificially generated downforce. No tricks, just pure physics. And the guy who actually strapped into this experimental machine and drove it upside down, that was Thomas Yates, the managing director of McMurtry Automotive. Just imagine the absolute unwavering trust you must have in your engineering team to sit inverted in a multi-million-dollar electric hypercar, relying on literally nothing but a vacuum system to keep you from crashing down to the floor. Yates called the 2,000 kilograms of downforce truly astonishing. And look, this stunt wasn't just for show. It was a very practical demonstration of exactly why this vehicle, the McMurtry Spéirling, has been absolutely shattering track records all over the world.
Okay, let's dive into this performance, because the numbers are staggering. 1.55 seconds. That's the time it takes the Spéirling to go from 0 to 60 miles per hour. 1.55. That is a blindingly fast, neck-snapping acceleration figure that just completely reshapes our understanding of mechanical grip. Now, it's powered by a pair of electric motors driving the rear wheels, pumping out exactly 986 horsepower. But here's the thing. Horsepower alone doesn't get a car off the line that fast without just spinning the tires into a massive cloud of smoke. You need grip. And grip requires immense weight, pushing those tires down into the asphalt.
And that brings us to the secret behind the speed. 4,409 pounds. That is the staggering amount of downforce this vehicle generates. But wait, here is the absolute most mind-boggling part of this entire metric. It generates that 4,409 pounds of downforce even while standing completely still. Think about that. A conventional Formula One car has to be traveling at incredible, blistering speeds for the air rushing over its wings to press it down into the track. The Spéirling, it doesn't need to be moving at all. It generates more downforce than its own physical weight at a dead stop.
Section 1. Engineering the vacuum. Let's look at how this actually works.
So, how exactly is this possible? Let's strip away the apparent magic of that upside-down stunt and reveal the pure math powering this beast. Tucked beneath the chassis, the Spéirling uses twin, high-speed centrifugal fans that spin up to an insane 23,000 RPM. Together, they pull roughly 60 kilowatts of power. To put that into perspective for a second, that's the equivalent power of about 40 heavy-duty household vacuum cleaners, all running at maximum capacity underneath this tiny little car. When you combine that with an underbody skirt system that seals the car right to the road, these fans pull air from a confined area beneath the chassis and blast it out the back. From an engineering standpoint, they're pulling a 52-inch water vacuum under there, which equates to about 1.9 pounds per square inch of vacuum spread across the entire 16-square-foot floor of the car.
So, the crucial point is how this actually compares to normal driving physics. If you're driving a standard, high-performance car at 100 miles per hour, the natural aerodynamic pressure under the car is only about 5 inches of water. The Spéirling's sealed fan system, it produces over 52 inches of water. That means this system multiplies the available aerodynamic pressure by roughly 10 times what natural aero produces at highway speeds. 10 times! You're essentially taking an entire racetrack's worth of aerodynamic load and packing it into just a few square feet underneath a single vehicle. It's brilliant.
Section 2. From prototype to production.
Now, what's really interesting about this slide is seeing how they translated this crazy prototype into a real product. For a long time, this level of performance was considered physically unattainable outside of some top-secret racing program. But McMurtry is actually putting a version of this car, called the Spéirling Pure, into production. It's a highly exclusive plug-and-play track car limited to just 100 units, and it's priced at a cool $1.3 million US. But to get from a record-breaking prototype to a usable product you can actually buy, the engineers had to adapt the physics. To give drivers meaningful track time, specifically enough juice to cover 31 miles at maximum racing pace, or about 20 minutes of driving, they had to bump the battery from a 60 kilowatt-hour pack to a 100 kilowatt-hour pack. And you can see the cascading effect this has on the engineering right here. The wheelbase had to grow by almost 8 inches just to fit the larger battery, and the overall weight went up by about 665 pounds. Yet even with that growth, the car remains incredibly compact. It's actually still shorter than a Mazda Miata.
Let's move to and see how this builds into our final topic, Section 3, the human toll.
Okay, so we've engineered a 986 horsepower vacuum chamber that blasts to 60 in 1.5 seconds and pulls 3 Gs during braking. But what happens to the human being strapped inside of it? When you map out the physical stressors on the driver, it's wild. At these near Formula One levels of performance, the human body is subjected to intense muscular effort, vibration, extreme thermal loads, and staggering G-forces. During cornering, those G-forces can reach up to 4 Gs. To put that in perspective, at 4 Gs, the driver's neck and shoulder muscles have to control a helmeted head mass of about 6.5 kilograms, which suddenly feels like it weighs 26 kilograms. That is nearly 60 pounds of force trying to rip your head sideways. The driver has to constantly fight just to maintain posture against these violent lateral and vertical forces.
And this brilliantly illustrates the internal cost of that fight. It carries a massive cardiovascular toll. As average track speeds and G-forces climb, driver heart rates absolutely rocket toward 200 beats per minute. And this isn't just from the physical exertion of turning the wheel or fighting those Gs, it's heavily influenced by the heat. Research actually shows that for every single degree your body temperature rises in a sweltering cockpit, your heart rate jumps by 25 beats per minute just to cope. Add in the emotional anxiety and the sheer adrenaline of navigating a $1.3 million hypercar at the absolute limit of adhesion, and the heart is literally working at its maximum capacity.
The sustained physiological punishment of driving a vehicle with this much grip is incredibly severe. Drivers operating at this extreme level can lose up to a full liter of fluid per hour, which leads to reduced circulating blood volume and very rapid dehydration. Their bodies are enduring massive, prolonged surges in stress hormones like cortisol and adrenaline. And then there's the inescapable vibration. To actually use that aerodynamic downforce effectively, track cars require unbelievably rigid suspension systems. That transfers brutal vertical loading directly into the driver's spine, creating a real risk for intraosseous disc herniations. The sheer violent constraints of a cockpit like this can even cause physical trauma, like nerve palsies, where drivers essentially lose function in their wrists or legs just from their nerves constantly banging against the rigid chassis. It is brutal. So here we are. We've reached an incredible era in automotive engineering. With twin centrifugal fans and a massive battery, we have successfully managed to stick a car to the ceiling and conquer gravity itself. We can calculate the exact dynamic pressures, dial in the fan curves, and extract limitless grip from a dead stop. But while our engineering scales to infinity, our biology? It remains exactly the same as it was thousands of years ago. The McMurtry Spéirling is an absolute triumph of human ingenuity, no doubt about it. But it leaves us with one deeply provocative question. Now that we've built a car that can break the laws of physics, is the human body the final speed limit? Thank you so much for joining me for this explainer, and I'll catch you next time.